life cycle of a star is a fascinating journey through various stages, marked by dramatic changes in structure, temperature, luminosity, and size. This process, spanning millions to billions of years, is driven by complex nuclear reactions and gravitational forces. In this detailed exploration, we'll examine the stages of stellar evolution, from the birth of a star in a nebula to its final demise as a white dwarf, neutron star, or black hole. Nebula, the stellar nursery. Stars begin their life in vast clouds of gas and dust called nebulae. These regions, often referred to as stellar nurseries, are composed primarily of hydrogen and helium with traces of heavier elements. The most famous examples include the Orion Nebula and the Eagle Nebula. Within these nebulae, regions of higher density can form due to turbulence, leading to the creation of protostars. Gravitational collapse. The process starts when gravitational forces cause a region of the nebula to collapse. As the gas and dust condense, the material heats up due to the conversion of gravitational potential energy into thermal energy. This creates a dense, hot core surrounded by a rotating disk of gas and dust. Protostar, the birth of a star. A protostar forms as the collapsing material continues to heat up. At this stage, it is not yet a star because nuclear fusion has not begun. Protostars are often obscured by the surrounding dust and are visible primarily in infrared light. Formation. As the core temperature reaches around 2000 Kelvin, hydrogen molecules start to dissociate into atomic hydrogen, increasing the core's opacity and trapping more heat. This raises the core temperature further, initiating the next stage in the star's life cycle. Main sequence, the stable period. When the core temperature reaches about 10 million Kelvin, hydrogen nuclei begin to fuse into helium, releasing enormous amounts of energy in the form of gamma-ray photons. This energy creates an outward pressure that balances the inward pull of gravity, stabilizing the star. This stage is known as the main sequence and can last billions of years. Hydrogen fusion. In stars like the Sun, hydrogen fusion occurs via the proton-proton chain reaction. In more massive stars, the CNO cycle, or carbon-nitrogen-oxygen cycle, dominates. The energy produced during fusion radiates outward, keeping the star in a stable, hydrostatic equilibrium. Post-main sequence red giant or supergiant. Once a star exhausts the hydrogen in its core, nuclear fusion ceases temporarily, causing the core to contract under gravity. The outer layers expand and cool, transforming the star into a red giant, or, for more massive stars, a supergiant. Helium fusion. In stars like the Sun, the core contracts until the temperature reaches around 100 million Kelvin, allowing helium fusion to begin. Helium nuclei fuse to form carbon and oxygen in a process known as the triple alpha process. In more massive stars, heavier elements can be formed through successive stages of nuclear fusion, leading to the production of elements up to iron. Example: Betelgeuse. Betelgeuse, a red supergiant in the constellation Orion, is an example of a star in this stage. It has expanded to a size hundreds of times that of the Sun, and will eventually end its life in a dramatic supernova explosion. Stellar death. The end of the road. The final stages of a star's life depend heavily on its initial mass. This determines whether it will become a white dwarf, neutron star, or black hole. Low to medium mass stars. White dwarfs. Stars with masses up to about 8 solar masses end their lives by shedding their outer layers, creating a planetary nebula. The remaining core, no longer undergoing fusion, becomes a white dwarf. These stellar remnants are incredibly dense and gradually cool over billions of years. High-mass stars, supernovae, and neutron stars, or black holes. For stars with masses greater than about 8 solar masses, the end is much more violent. Once iron forms in the core, fusion ceases, leading to a catastrophic collapse. This collapse results in a supernova explosion, dispersing heavy elements into space and leaving behind either a neutron star or a black hole. Neutron stars. If the remaining core is between 1.4 and about 3 solar masses, it becomes a neutron star. These objects are incredibly dense, with a teaspoon of neutron star material weighing billions of tons on Earth. Black holes. For cores exceeding about 3 solar masses, the collapse continues until a black hole forms. Black holes have such strong gravitational fields that not even light can escape from them. The cycle continues. The material ejected from dying stars contributes to the interstellar medium, enriching it with heavy elements. These elements are crucial for the formation of new stars, planets, and ultimately life. This cyclical process ensures that the universe remains dynamic and ever-changing. Detailed analysis of stellar evolution. To understand stellar evolution in detail, we need to examine the processes at play during each stage of a star's life. The primary source of a star's energy is nuclear fusion. During the main sequence, hydrogen nuclei fuse to form helium in a process that releases energy according to Einstein's equation, E=mc². In the Sun, this occurs via the proton-proton chain. 1. 2 protons fuse to form a deuterium nucleus, a positron, and a neutrino. 2. The deuterium nucleus fuses with another proton to form helium-3 and a gamma-ray photon. 3. 2 helium-3 nuclei fuse to form helium-4 and 2 protons. In more massive stars, the CNO cycle plays a significant role. 1. Carbon-12 captures a proton, becoming nitrogen-13. 2. Nitrogen-13 decays to carbon-13, emitting a positron and a neutrino. 3. Carbon-13 captures a proton, becoming nitrogen-14. 4. Nitrogen-14 captures another proton, becoming oxygen-15. 5. Oxygen-15 decays to nitrogen-15, emitting a positron and a neutrino. 6. Nitrogen-15 captures a proton and splits into carbon-12 and helium-4. As stars evolve, they synthesize heavier elements through nuclear fusion. The triple alpha process, which converts helium into carbon, is essential for the creation of elements beyond helium. In more massive stars, nucleosynthesis proceeds through a series of fusion reactions, producing elements up to iron. Beyond iron, energy must be supplied rather than released to create heavier elements. This occurs during supernova explosions, where the intense conditions allow for the formation of elements heavier than iron through rapid neutron capture, or R process. White dwarfs, neutron stars, and black holes are characterized by their degenerate matter. Composed of electron degenerate matter, white dwarfs are stabilized by electron degeneracy pressure. The Chandrasekhar limit, about 1.4 solar masses, is the maximum mass a white dwarf can have before collapsing further. These stars are supported by neutron degeneracy pressure, with densities comparable to atomic nuclei. When a stellar core exceeds the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses, neutron degeneracy pressure cannot prevent further collapse, leading to the formation of a black hole. Observational evidence and theoretical models. Astronomers rely on observational data and theoretical models to study stellar evolution. Observations of star clusters, supernova remnants, and variable stars provide insights into different stages of stellar life cycles. The Hertzsprung-Russell, or HR diagram, is a vital tool in this research. plotting stars' luminosities against their surface temperatures and revealing their evolutionary paths. Star clusters are particularly useful for studying stellar evolution because they contain stars of similar ages and compositions. By comparing stars in clusters of different ages, astronomers can trace the evolutionary sequences of stars. The remnants of supernova explosions, such as the Crab Nebula, offer a glimpse into the end stages of massive stars. These remnants help researchers understand the processes that occur during and after a supernova. Certain types of variable stars, like Cepheids and RR Lyrae stars, have well-defined relationships between their luminosity and pulsation periods. These stars serve as important distance indicators and provide clues about stellar structure and evolution. Impact on the universe. Stellar evolution plays a critical role in shaping the universe. The elements synthesized in stars are the building blocks of planets and life. Supernova explosions distribute these elements into space, enriching the interstellar medium and triggering the formation of new stars. Chemical enrichment. The process of stellar nucleosynthesis and the subsequent dispersal of elements by supernovae are responsible for the chemical diversity observed in the universe. Elements like carbon, nitrogen, oxygen, and iron, essential for life, are produced in stars and distributed through these cataclysmic events. Star formation. The death of stars, especially in supernova explosions, compresses nearby gas clouds, promoting the formation of new stars. This cyclical process ensures a continuous supply of material for new stellar generations. Illustrative examples. The Orion Nebula. Located about 1,344 light-years away, the Orion Nebula is one of the most studied star-forming regions. Within this massive cloud of gas and dust, new stars are constantly being born. The Hubble Space Telescope has captured stunning images of the Orion Nebula, revealing its complex structure and the young, hot stars that illuminate it. The Crab Nebula. A famous supernova remnant, the Crab Nebula is the result of a supernova explosion observed in 1054 AD. It contains a neutron star at its center, which is a pulsar emitting beams of radiation. This remnant provides crucial insights into the processes that occur during and after a supernova explosion. Globular clusters. These are tightly bound groups of stars that orbit the galactic core. An example is the globular cluster M13, which contains hundreds of thousands of stars. Studying these clusters helps astronomers understand stellar evolution, as they contain stars of different masses but similar ages and compositions. Stellar evolution in different mass regimes. The mass of a star is the most significant factor determining its evolutionary path. Let's delve into the specific life cycles of low mass, intermediate mass, and high mass stars. Low mass stars, up to 0.5 solar masses. Formation and main sequence. Low mass stars, like red dwarfs, form from smaller regions of molecular clouds. They have lower temperatures and luminosities compared to more massive stars, and burn their fuel very slowly, allowing them to remain on the main sequence for tens to hundreds of billions of years. End stages. Due to their low mass, these stars never reach the temperatures necessary for helium fusion. Instead, they will eventually exhaust their hydrogen fuel, cool, and contract into white dwarfs without undergoing a red giant phase. The white dwarfs formed from low-mass stars are composed mainly of helium. Intermediate mass stars, 0.5 to 8 solar masses. Main sequence and red giant phase. Stars like our Sun fall into this category. They spend the majority of their lives fusing hydrogen into helium in their cores. Once the hydrogen is exhausted, the core contracts, and the outer layers expand, forming a red giant. During the red giant phase, the core temperature increases, allowing helium fusion to begin, forming carbon and oxygen. Planetary nebula and white dwarf. Eventually, the outer layers are ejected, creating a planetary nebula. The remaining core becomes a white dwarf, composed primarily of carbon and oxygen. Over billions of years, the white dwarf will cool and fade. Example: the Sun. The Sun, an intermediate mass star, will eventually enter the red giant phase, expanding to engulf the inner planets, including Earth. After shedding its outer layers, it will leave behind a white dwarf. High-mass stars, above 8 solar masses. Main sequence and supergiant phase. High-mass stars, such as those found in the upper left of the HR diagram, have short, intense lifespans. They burn through their nuclear fuel quickly due to their high luminosities and temperatures. After exhausting their hydrogen, these stars enter the supergiant phase, where they fuse heavier elements in their cores. Supernova explosion. When the core consists of iron, fusion stops, leading to a gravitational collapse. This results in a supernova explosion, dispersing elements into space and leaving behind either a neutron star or a black hole. Neutron stars and black holes. The remnants depend on the core mass post-supernova. Cores between 1.4 and about 3 solar masses form neutron stars, while more massive cores form black holes. Neutron stars are incredibly dense, with radii of about 10 kilometers, but masses exceeding that of the Sun. Black holes, on the other hand, are regions of space with gravitational fields so strong that not even light can escape. Astronomers categorize stars into different populations based on their metallicity, which is the abundance of elements heavier than helium, and their location within the galaxy. These categories help in understanding stellar evolution in a broader galactic context. Population-wise stars are metal-rich stars, like the Sun, found in the galactic disk. They are relatively young and have formed from gas clouds enriched by previous generations of stars. Population-wise stars are crucial for studying ongoing star formation and galactic evolution. Population 2 stars, on the other hand, are metal-poor and older, typically found in the galactic halo and globular clusters. Their low metallicity indicates that they formed early in the galaxy's history, providing insights into the conditions of the early universe. Now, population 3 stars are theoretical and have not yet been observed. They are believed to be the first generation of stars formed after the Big Bang. These stars would have been composed almost entirely of hydrogen and helium, with no heavier elements. Understanding these stars is key to studying the early stages of stellar and galactic formation. The role of binary and multiple star systems. Many stars are not solitary, but exist in binary or multiple systems. Interactions between stars in such systems can significantly alter their evolutionary paths. Mass transfer and accretion. In close binary systems, a star can transfer mass to its companion, affecting both stars' evolution. For instance, a white dwarf in a binary system can accrete matter from a companion, potentially leading to a Type Ia supernova if it exceeds the Chandrasekhar limit. Mergers. Stellar mergers, where two stars collide and combine, can result in unusual and massive stars. Such events can produce blue stragglers in star clusters, which appear younger and more massive than other stars in the same cluster. Example: Sirius system. The Sirius star system consists of a main sequence star, Sirius A, and a white dwarf companion, Sirius B. The evolution of Sirius B influenced the system's dynamics and provides a case study for binary star evolution. Modern tools and techniques in stellar astronomy. Advancements in technology have revolutionized the study of stellar evolution. Observatories and telescopes, both ground-based and space-based, play a crucial role. Space telescopes. Instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and the James Webb Space Telescope provide high-resolution images and spectra across various wavelengths, from ultraviolet to infrared. These observations are critical for studying star-forming regions, stellar remnants, and the detailed structure of stars. Spectroscopy. Spectroscopic analysis allows astronomers to determine a star's composition, temperature, velocity, and other properties. By examining the absorption and emission lines in a star's spectrum, researchers can infer its chemical makeup and evolutionary stage. Asteroseismology. This technique studies the oscillations and pulsations of stars, providing insights into their internal structure. By analyzing how stars vibrate, scientists can infer details about their cores, compositions, and ages. Computational modeling. Numerical simulations and computational models are essential for understanding the complex processes of stellar evolution. These models incorporate physical principles such as nuclear fusion, radiative transfer, and fluid dynamics to predict how stars evolve over time. The future of stellar evolution research. Ongoing and future missions promise to deepen our understanding of stellar evolution. Next-generation telescopes. Upcoming observatories like the Extremely Large Telescope, ELT, and the Large Synoptic Survey Telescope, LSST, will provide unprecedented resolution and sensitivity. These instruments will enable detailed studies of distant star-forming regions, supernova remnants, and stellar populations in other galaxies. Gravitational wave astronomy. The detection of gravitational waves from events like binary neutron star mergers opens a new window into studying stellar remnants and the end stages of stellar evolution. Observatories like LIGO and Virgo are leading this field, with future enhancements expected to increase sensitivity and detection rates. Exoplanet research studying planets around other stars, known as exoplanets, also contributes to our understanding of stellar evolution. Observations of exoplanet systems provide insights into star-planet interactions, the influence of stellar activity on planetary atmospheres, and the potential for life in different stellar environments. Conclusion. The life cycle of a star, from its formation in a nebula to its eventual demise as a white dwarf, neutron star, or black hole, is a complex and awe-inspiring process. Each stage of a star's life is governed by fundamental physical principles and contributes to the dynamic evolution of the universe. Through observations, theoretical models, and advanced technologies, astronomers continue to unravel the mysteries of stellar evolution, providing a deeper understanding of the cosmos and our place within it. This detailed exploration of the stellar life cycle highlights the intricate and interconnected processes that shape the universe. From the birth of stars in nebulae to their explosive deaths and the formation of exotic remnants, the journey of a star is a testament to the power and beauty of nature's fundamental forces. As we continue to explore and study these celestial phenomena, we gain not only scientific knowledge, but also a profound appreciation for the wonders of the universe.